So this is our last lecture before the exam on Exergy. And all right, let's jump into it. Let's solve this problem. So we have steam at a given flow rate of 0.3 kilograms per second, given temperature and pressure, flows through a, right away, a throttling valve, throttling device. You should know that. You say, aha, I've analyzed these before. I know what's going on. I had them in Thermo 1. I see them again in Thermo 2. And it exits at a given pressure. So we're given a flow rate, inlet temperature, inlet pressure, exit pressure. Do they give me things about exit elevation, inlet elevation? No. How about inlet speed, exit speed? No. So right away you're thinking, ignore the effects of motion, kinetic energy effects, and gravity, potential energy effects. Okay, so, but they only give me the pressure on the exit. All right. So we have the dead state temperature and dead state pressure. And so maybe we organize the information. Maybe we make a sketch. Is that a good sketch of a throttling valve? Sometimes you put a little like what controls it up here. So inlet state 1, outlet state 2. Make your traditional list of properties because you're working with states. You can do the pressure, the temperature, the internal energy, the enthalpy. I forgot the specific volume, tuck that in. Specific volume, internal energy, enthalpy, entropy, flow exergy, and some more if you want. Okay, so you can talk about it at state 1, as well as the pressure at state 2, the temperature at state 2, the specific volume at state 2. This is 1, U1, U2, H1, H2, S1, S2, EF1, EF2. Even before we uncover what we're asked to find, you should be able to think through this problem. Do you know enough about throttling devices? What happens to the pressure? What does P2 do? Is P2 greater than P? Oh, sorry. Is it greater than P1, equal to P1, less than P1? You see my kind of question, how I'm phrasing that? What does the pressure do? It drops. With confidence, or they need to tell me in the problem statement? They're confirming it when you look at the value here, 60 bar and 20 bar. It's confirming it, but man, if it didn't drop, I've got a bad throttling problem. It's going to drop. How about the temperature? Those are a little more dicey, right? Could go up or down, but depending, it really does depend. A lot of times it goes down. Specific volume probably expands a little bit, takes more space. The specific volume goes up. How about the internal energy? How about the enthalpy? How about the entropy? How about the flow exergy? I tell you what, I'm not going to give you the answers because it's going to cheat you of your education. So I'm going to do this. I'm going to say that probably on an exam like this, we're going to have that you need to be able to solve for the rate of exergy destruction in the valve. Do you think that would be positive, negative, or equal to 0? What do you think the rate of exergy destruction in the valve is going to be? Positive. And it's going to be positive 40.6 kilowatts. When would you expect it to be 0? When would you expect the exergy destruction rate to be 0? If there's no irreversibilities, and basically you're always going to have irreversibilities in an expansion valve. All right? So, and if you ever calculated a negative exergy destruction rate, what should you look for? Your error. You got an error somewhere. All right. So now that you can calculate that, what is the annual cost of the destroyed energy, assuming that it runs for 8,400 hours of operation per year? So basically there's flow going through this through the whole year, and there's 8,400 hours of flow through that device per year. And the cost of the energy is 2 cents a kilowatt hour, which is really cheap energy. So you have to take that exergy destruction rate multiply it by how many hours are in a year, that will give you the total amount of energy that has been wasted, so to speak. The exergy has been destroyed. That useful part of the energy has been wasted or destroyed. And you multiply that by the cost per unit of energy. All right, so basically you'd have 40.6 kilowatts times 8,400 hours per year. What do you get up here? Kilowatt times an hour is a great unit of measure of energy. And if you look at your CPS bills, when you purchase electricity, you'll see how many kilowatt hours of electricity you consumed in your house or apartment in that billing period, typically about a 30-day billing period. Anybody look at their CPS bill? Only one? Really? 2? That's it? How about go look at your parents' bill? I remember one friend of ours, she said when she moved to a different city, she got upset. She called back to her dad and said, "Dad, in this city they charge us for water. I can't believe it, Dad." So anyway, yeah, the units of that they charge us for electricity is kilowatt hours. And it's around 10 cents you pay, residential rate, San Antonio. You go to Houston, a little more. Go to Hawaii, a lot more on unit electricity cost. All right, now we continue on and we say that it's a 2 cents. Is that a way of writing 2 cents, 2 pennies? Yeah. $0.02 per kilowatt hour of energy. And then you'll see that these cancel. And you'll be left with dollars that you have to pay per year, and it's equivalent to $6,815 per year. All right. I'm leaving you high and dry. There's the answers. You need to solve it. I really want you to focus on what's the relationship between these, and these, not this necessarily. You can look at also V1 and V2, but that's not necessarily as important. These are the real important ones that you got to get straight in your mind. Okay? All right. How do you like that? He refuses to teach. All right. 2 kilograms of oxygen in a piston-cylinder assembly. As soon as you see these key words, what are you thinking? Closed system. How many points partial credit are you going to get if you start with an open system analysis of a piston cylinder? Not much. You're going to cry and you're going to complain about me. I'm telling you right up front. It's open. If you want a closed, no equation sheet exam, then I'm more than happy to give more partial credit. But there you go. So we have 2 kilograms of oxygen. It's in a piston cylinder assembly. It's initially at this pressure, 1.5 bar, this temperature, 27 degrees C. It is heated at constant pressure. How can you heat something and still maintain constant pressure during the heating process? Let the volume expand. And then the students always, when I teach Thermo 1, it is a mind trip. It's like, okay, this is where the piston is at state 1. Later, the piston's up here at state 2. The weight of the piston has not changed during the process. We've applied some heat right here. And maybe I'd try and draw a flame. I don't know if I could draw a flame that well. So I have some heat transfer going into it. And I ask them, what about the pressure, the final pressure at the end of the heating process? And they say, the piston's at a higher elevation. It has to be a higher pressure. I get about a third of them will say that. 2/3 will say, nah, you didn't trip me up. I took statics. I could draw a free body diagram of that piston, isolate it. When I do, I have the weight coming down, I have atmospheric pressure coming down, and I have the pressure below pushing up. And guess what? The elevation of the piston doesn't come into play. And so the pressure at 1 is, I can conclude with confidence that it's equal to the pressure at 2. Right? Right, so there you go. So that's how you can easily have this heating at constant pressure. It makes sense. in a piston cylinder where the piston can rise in a gravitational field. All right. There are no internal irreversibilities. Right away, what does that mean? There's no internal irreversibilities. No entropy production or exergy destruction. One way you can say that would be like sigma dot equal to, or not sigma dot, sorry, sigma equal to 0, because it's a closed system. You're going to be doing a process from initial state 1 to 2. If you want to put a subscript 1, 2 on there, that's fine. Or you could put that exergy destruction 1 to 2 is 0, also 0. All right. It's heated till it attains a final temperature. Well, tell me a little bit about this initial temperature. It started at 27 and it ends up at 227 degrees C. What happened to the oxygen? It got hotter because of the heating. It expanded because of the heating, but the pressure stayed constant. You got the dead state temperature and pressure given. Ignore the effects of motion and gravity, meaning negligible. Somebody might say, look, I have this system and it has a center of gravity right there. And now I have expanded it, and you put it like that. Let me change color on that. And now I have the center of gravity a little higher. Neglect that. Change the center of gravity of the chunk of oxygen. That's what they're saying right here. Neglect that. Okay? All right, for an ideal gas, can you determine the work done? What's our system? Our system is the focus of the study. It's the oxygen trapped in the piston cylinder assembly. Is the piston part of the system? No. The piston's part of the surroundings. Go back to like chapter 1, 2, or 3 of this textbook, and they have a problem where let's make now the system include the piston. No, let's make the system exclude the piston, and it's only the gas. All right? The best system, the most common system for these is just the trapped gas. All right. If you'll have a question about that, come talk to me and I'll show you where it's at. It's a good example problem to struggle through in Thermo 1. So anyway, the focus is on the closed system, which is just the oxygen only. All right. So what is the work that the oxygen does? Does the oxygen do any work during the process? Yeah. What type of work? How do I describe that work? Shaft work? No. What type of work? I'm looking for one word in front of that. Boundary work. What does boundary work mean? It's an expansion work. I'm pushing back the face of the piston, pushing it back. So how do I calculate that work? 1 to 2. From first principles, it's the integral of f dx. Do you remember integral f dx in mechanics? Yeah, some of you even have it tattooed on your bodies. I see it all the time. Right there next to E is equal to mc squared. You're so proud of that equation, you mastered it. So anyway, you multiply by A and you divide by A, and this f dx becomes the integral P dV. Cross-sectional area of the piston, you're pushing it back through a distance dx. Hey, that's a dV, integral P dV. So for this problem, I'd like to calculate the integral P dV. Well, is P constant? Yes or no? Yes, it is. So is it just P times the final volume minus the initial volume? Sure. And then I look at this problem a long time. They give me 2 kilograms of oxygen. Well, I can do it. I can calculate it like P times M lowercase v2 minus v1. Or I can calculate it P times N v2 bar minus v1 bar. I have to know what each of these little notations mean. What does this lowercase m right there mean? It's the mass, and it's 2 kilograms. What is this v here? Specific volume. What would be the units on that specific volume? Meter cubed per kilogram, and so the kilograms are going to cancel. That's right. Now I come over here, this n and this v bar. So what is the n? The number of kilomoles. The amount. Instead of mass, it's amount. It's a number of kilomoles. And what is this V bar? It's the no, it's not the average. Some classes we use the bar for the average. But what is the V bar? It's not per kilogram. It's the volume per amount of meter cubed per kilomole. Are you joking me, Professor? Yeah, no, I'm not joking you. We can work this problem in the mass perspective or amount perspective. How would I calculate V1? How would I calculate V1? How does this always behave? Ideal gas. Can I use the ideal gas equation? Is P1 V1 equal to RT1? And if that's on a mass basis or on a molar basis, is P1 V1 bar equal to R bar T1? Yes or no? Do you like both of these equations? You can see where one equation works. What's the difference between this R and that R? There's a bar on one of them. Are they the same? No, they're not the same. What's the relationship between the two? The molar mass. Exactly right. So, what's the relationship between M and N? The mass here, used over there, and the amount N. What's the relationship? Is that the relationship? Or is that the relationship? First of all, what's big M? Molar mass. All right, I'm going to pause, walk around. I want to see which one of these is correct. This one or this one? If I wanted to get the mass and I knew the number of moles, which way do I go? Do I multiply by M or do I divide by M? So that's the correct representation. If you just chase the units, you'll have kilomole, and then the molar mass would be how many kilograms per kilomole, and then they cancel, and then you're going to be left with the units of kilogram over here. So you can choose to stay in a mass description or a molar description. The only thing is for this first part for the work, it's no big deal. Either one works, okay? But when we get to the heat transfer, how am I going to calculate the heat transfer? Oh, did you want answers for this so that you can check your numbers later? The work is 104 kilojoules. Okay, what about the heat transfer? How are you going to calculate the heat transfer? I'm going to pause. I really want you to do it. All right, so let me pick it up. Somebody says, I'm going to write the first law. I'm going to have a change in enthalpy equal to the heat transfer in 1 to 2 plus the work 1 to 2. Do you like that equation? Does it have an error? Yes. It has an error. Who wants to volunteer to tell me the error? One student. Right back there. It is definitely not enthalpies when you write down the first law for a closed system. It's internal energies, and it's a common mistake people make. All right? So you've got to get your equations right. Now, the other one, there's another small error. Minus sign. Because the sign convention is Q in, work out. All right. So in this problem, we just calculated this work. You can just leave it and substitute in for that work value. And now I need to calculate the delta U. How am I going to calculate the change in, and this is cap U or lowercase u? Cap U. It's the change in the total internal energy. So how am I going to calculate? Is that the same as writing cap U2 minus cap U1? Yeah, right. So how am I going to calculate that? Is it the mass times lowercase u2 minus u1? Yeah. Is that the mass times c sub p T2 minus T1? You're good. Did you hear your friend call that out? What did they say? Not CP, but CV. But CV, very good, very good. So it's C sub V. Now the challenge is can I get C sub V for oxygen? You can, it's temperature dependent. If you look at our temperatures, this starts at 300 Kelvin and ends at 500 Kelvin. So during the process, what would be the good average temperature for the oxygen? Starts at 300, ends at 500? 400. You're an engineer. We make approximations. All right. Don't need to explain that one to most people. They got that one down. Somebody says, I want to calculate this using the tables. I really want to use the table. Table A22. Ideal gas properties and oxygen's in there. You can. But you get U bar 2 minus U bar 1. That U bar 2 is evaluated at what temperature? 500 Kelvin. And this U bar 1 at 300 Kelvin. Do you see that in table A22? U bars instead of U without the bar. Look at the header in the table. What's it say for the units on that U bar? Kilojoules per kilomole. So do I multiply by M or multiply by N? And you can go back and forth between M and N. No problem. I have the molar mass of oxygen. What's the molar mass of oxygen? 16 and 16, roughly 32. You want more digits? Look it up in the table. But it may be 32.00 if my memory is correct. All right. So somebody could say, well, if I put the number of moles, CV bar times T2 minus T1, will that also work? But I now got to get the specific heat, constant volume, not on a mass basis, but on a molar basis. Yes, that'll work as well. So anyway, this is probably a good one, and this is a great one too. But either one, when you make the calculation, you find that the answer comes in at around 377 kilojoules. Somebody says, look, if I take this W and throw it over here, let me scroll down, because I have the Q1 to 2 is equal to U2 minus U1, and then I have this plus W1 to 2. I bring that to the other side, right? But wasn't that W1 to 2 P 2 times V2 minus P1 times V1? And then I lump so that I get the U2 plus P2 V2 minus U1 plus P1 V1. And then they say, look, there's H2 minus H1. I thought you said we would never see the enthalpies when we're working with closed systems. This is one of those cases. If you have constant pressure boundary work, the amount of heat brought in is equal to the change in H. Because you didn't have to worry about that constant boundary work. It can be lumped just like I did. This constant boundary can be lumped with the delta U to get delta H. But if you write that Q is equal to delta H plus W1 to 2, you're wrong. You already counted for it. See that? So somebody else could say, oh, that Q1 to 2 is equal to the mass times H2 minus H1. It's the same game. It's like this whole thing stretched out. Sure, you're right. How about the mass times C sub P, T2 minus T1? You're right. Is it equal to the number of moles times H bar 2 minus H bar 1? You're right. How about number of moles times the C sub P bar times T2 minus T1? You're right. I'm not trying to confuse you. I'm just showing you there's a lot of ways people can solve the problem correctly. All right, I need to press forward. Now, what about this last part C? What is the Exergy transfer accompanying that work transfer? There was 104 kilojoules of work. It was boundary work. The gas expanded, pushing back the piston. From the perspective of the oxygen, what is the exergy transfer that accompanies that work? Pardon? Okay, 3 answers. You can say it's equal to the work, which is 104 kilojoules. It's less than the work, so it's going to be less than 104 kilojoules, or it's going to be greater than the work, greater than 104 kilojoules. Which one is it going to be? Go back to the description of what exergy was. Was it 100% of the work transfer or only the useful work? Is pushing back the atmosphere useful? Is pushing back the atmosphere useful? No. Pushing back the atmosphere is not useful. So, did you push back the atmosphere? You did. What was the work associated with pushing back the atmosphere? The work not useful was also a boundary work, but it was the integral of P naught dV. Not P dV, but P naught. Because the atmosphere is at pressure P naught. It's just pushing back the atmosphere. So this work, pushing back the atmosphere, is not as big as pushing back the piston. All right, so what is the non-useful? It's around 69.3 kilojoules. And so you did 104, but 69.3 didn't count. And so the work, exergy transfer with the work comes in around 34.6 kilojoules. All right, last part. What is the exergy transfer with the heat transfer? How are we going to calculate that? Well, your mind may say, look it, I'm going to have the exergy transfer with the heat transfer. That will be some sort of integral 1 minus T naught over TB del Q during the process. But what's happening is the temperature of the gas, the boundary temperature, is continuing to change from 300 to 500. This is a doable integral, but it will test your calculus capabilities. Now, do engineers like to really demonstrate their Cal 2 capabilities, or do they like to look for an alternative strategy to calculate this without doing an integral? They look for an alternative strategy. So they go to a not first principle, how to calculate the exergy transfer with the heat transfer. They go back to an exergy balance. And so you say, we have the change, let's say the final exergy minus the initial exergy. I'm going to put an EX to emphasize it's the final exergy minus the initial exergy during that process is equal to what is the exergy transferred in with the heat during the process minus the exergy transferred out with the work during the process plus or minus the exergy being destroyed during the process. Did we just calculate the exergy transfer with the work during the process in part C? Part C, yeah. The key words right here, no internal irreversibilities. What does it say about this term right there? 0. Now I have this is equal to a change in exergy. I just need to calculate the change in the exergy. So the exergy transfer with the heat transfer, depending on what symbol you like, I put a cap Q there and a lowercase q, but anyway, it's the same. We're going to have that it's going to be the mass times U2 minus U1 plus P naught V2 minus V1 minus T naught S2 minus S1. True? And then you go back and you struggle with these we've done. Internal energies we've talked about, but we haven't talked about the changes in the entropy, have we, for an ideal gas, the oxygen. How do I get the change in the S for the oxygen? S2 minus S1 needed right there. How do I calculate that? Well, S2 minus S1 is equal to S2 naught minus S1 naught minus R natural log of P2 over P1. True or false? Look good? Do I have an error in it? Look good? Remember that equation? Out of Thermo 1, how to calculate the entropy change for an ideal gas. Well, right away, our pressure isn't changing, so this term is very simple. The natural log of 1 is 0. Very good. And then where do we get this S naught? Well, if you want, you can put a bar over it and a bar over it and get that out of the table A22, but then you would need to do this equation. Do N U bar 2 minus U bar 1 plus P naught V bar 2 minus V bar 1 minus T naught S bar 2 minus S bar 1. A little easier probably when you do the entropy calculations to use on a molar basis. Make sense? Long, tedious problem. Did we solve one like that in our homework? You even know the problem number, huh? Which problem number was it? 7 something? Anyway, please be able to solve closed system problems as well as open system problems for the exam on Monday. Thank you.